Yes, let's do this, shall we? We have a quiz to go over. Excuse me. It's not really a quiz. That's what Icon calls it. They don't have a formative assessment category, but again, I grade these to see that you've made an attempt, not for effort, and also to see if there's any common threads in people's misconceptions. But let's do this one here. By the way, I set these up so that you can do multiple attempts. So if you wanted to go back in and like make another attempt and write things down to take notes as we go so that you have them, that's totally fine with me, or you can write the answers down however you want. So first one here, given that the relationship between a single quantitative or binary predictor with a single quantitative outcome is the same as a bivariate Pearson's correlation, what is the reason to estimate it using a general linear model, i.e. linear regression, instead? So what do you think? Prediction, yes. Keep talking.
Correlation is just a connection between the two.
Mm-hmm.
And regression is like
Yes, although you could say that if X and Y are correlated, X predicts Y or Y predicts X, design would say whether or not like you can say one goes first. But along those lines, what other kinds of things can we do with respect to prediction that we can't do with just correlation?
You can look at the individual. You can't really look at the individual correlation.
Look at the individual, like figure out what their predicted outcome is?
Yeah, for
Okay.
like each individual instead of looking at a bigger picture.
Yes, I think technically you could work out the correlation
Yeah.
to do that, but the model makes it more explicit.
Mm-hmm.
All true, but still not where I was going. There's one more thing that's the big one.
You can make more predictions.
More predictions. Yes, keep talking.
So, because like if you're in a correlation, it's just the two.
Mm-hmm. Just
But you can,
bivariate.
like, add more things.
Yes, more
into-
predictors.
To regress more predictors.
Yes.
Into your regression.
Yes, yes, yes. So there's sort of two main answers I was thinking of. One is that the idea that you could add multiple predictors at the same time, and we're not there yet, but that's where we're headed. So I'm foreshadowing. See, and the idea of looking at whether or not each one still predicts the outcome after you factor in the others. So the idea of unique prediction. Another one has to do with, I'll give you a hint, the idea of linearity. So Pearson's correlation assumes a linear relationship, right? And we said it's not a valid or reasonable thing to do if there's a nonlinear relationship. And the question is, what do you do instead? A model. So that is this is going to be the second part of example 3, or example 5 is looking at how to model nonlinear effects of quantitative predictors, because correlation doesn't do that for you in any way, shape, or form. So anyone come up with any others? Okay, cool. All right, so definitions. This is vocabulary. This is the kind of thing that just has to roll off your head eventually, and it takes practice and it takes repetition. But in a GLM, predicting Y from a single predictor X, so that right there, right? Decomposing that, right? When I said that, did that immediately make sense to you? Ish. So in a GLM, what's that?
General linear model.
General linear model. General linear models are for predicting quantitative outcomes using the normal distribution. So that right there is one thought. Predicting Y is an outcome, so that's my notation. Y always means the thing to be predicted or explained from a single predictor X. So there I'm trying to help you. I could have just said from a single X, and I would have meant predictor X. Define each of the following. So fixed intercept, which is always going to be beta 0. What's that?
It's the Y value when X equals 0.
The Y value when X, all the X's, right now we only have one, but when all of them equal 0. Yep, very good. That is from algebra, that'd be like Y equals mx plus b, that's b. But b, I mean, that just don't pretend you never learned that though, because that system of notation is different, but it's the same concept. It's the constant or whatever. Fixed slope for X beta 1. So I'm looking for a generic definition that would hold for any kind of X. So this would be the m in the aforementioned equation. What do you think? Alfonso, I'm calling on you.
It's the increase in y for 1 unit change in x.
Yes, it's the increase in y for a 1 unit change in x. That is absolutely correct, but I'm going to make a slight adjustment on that. So my area of expertise in quantitative methods is longitudinal analysis, so people who are studying change over time. So I tend to use I tend to make a difference between a change in y versus a difference in y, because change to me implies that like one person is actually changing over time as opposed to just going higher or lower. So you will hear me say a 1 unit difference in y for a 1 unit difference in x because it's a cross-sectional analysis. But no one would say you're wrong if you say a change in y per unit change in x. That's just the language. But it's just one of those like little nitpicky jargon things that I tend to make that distinction. But yes, change in y for a 1 unit change in x. So you got to know what a unit is for that to make sense. If your x predictor is a binary variable, then you're talking about the difference between the 0 group and the 1 group as the unit change. What if your x was a proportion? Like the proportion of days in which you're having a hacking cough or something, right? Which for me was like, most of the last month or something. 70.75 of the days I've had a hacking cough. If your variable was like that, then what is a unit? Cough drop?
Oh, that'd be wonderful. Terrific. Thank you.
No problem. I got Kleenex too if you need some. I'm a walking Walgreens, So yeah, if you have a proportion, no, you can keep it for now.
Oh, no, thank you.
All right. Anyone else? I want to share. It's not Halloween candy yet. It's cough drops, but. So yeah, if your x is a proportion, then a unit is all the way between like none and all of it, right? So then you would have a coefficient that's probably pretty big because it's the difference between the entire theoretical range of the variable. So just keep that in mind in what a unit means. It can be convenient to rescale your variables so that a unit is something that is easier to work with. So depending on the time scale, you might have like decades versus days versus weeks, like how far apart in time things are, for instance. In terms of money, like the outcome we're looking at is scaled in thousands, so the numbers aren't so ridiculous that they're hard to keep track of. So, and then last but not least, the residual E. Give me another word that translates to residual.
Error.
Error, that's what E comes from. But what is an E?
It's the difference from what is observed from what is expected.
Yes, the difference between what is observed, the original y sub I, and what is expected or predicted. You can think of those as synonyms. Expected value is sort of a math term, but predicted value. What is the symbol for the predicted y, by the way? Hat. Yes, the caret thing. Y hat. Very good. There. You got it. So honestly, that's it. I mean, you know what these three things mean. You're home free. That's it. The additional complexity comes in making sure that for each type of x, you know what to do with it. And so far, we've only had one, but that changes today. It'll be okay. It will, I promise. I promise. What is the reason for centering model predictors? Have a meaningful zero value of the predictor so that what also makes sense?
Where the slope starts?
Yeah, where the intercept is, yeah, because the intercept is always the expected outcome when x equals 0, so you don't want that to be some place where there is no x that could possibly be 0. So centering, the definition of that term, what does that mean again? Adding or subtracting a constant. So it's a linear transformation, just shifting the scale of the variable. So which model effects or properties should change as a function of centering and which should stay the same? I'll give you a hint, there's only one thing that changes. The intercept and the intercept's estimate and what else? Jing, I think you sent me this question via email. Because you weren't getting it right in your homework, and this was the reason why. Do you remember?
Different center differences and we got different intercepts.
Say that again?
When we center it to different numbers, we get different intercepts.
You get different intercept estimates and standard errors. Remember the, here's my bag. Show and tell time, the fulcrum idea, right?
Yeah.
Yeah. So she had an incorrect answer because she forgot to center her predictor. So in homework 3, you're centering please count at 7 and fit count at 5 in various models. So if you don't have the right intercept, it's like, where are you slicing your slope at? And that's going to be a different point depending on where x is 0, and it's going to be a different width around it based on this sort of idea. So yes. In my homeworks, I typically will start asking you from now on if you have the residual variance correct in your models. If that is correct, you have the right things in your models, right predictors. I will also ask you for the fixed intercept. If you have the fixed intercept right, then you know that your predictors are all centered at the right place. So it's 2 different sorts of diagnostics that you'll start to see. And I do this in my advanced classes as well. Okay. So yeah, everything else stays the same. How good the model is, how you interpret the slope, doesn't depend on where you center it. That only comes into play in more complex models that we haven't gotten to yet. So, but we will. All right, last but not least, how do unstandardized fixed slopes, e.g. beta 1, effect sizes such as R, and test statistics such as T, relate to each other and to sample size? I meant that to be sort of amorphous, because these are all sort of things that are related and kind of floating around together, right? So we'll start with the sample size part. Which of these things are dependent on n? We got unstandardized slopes, effect sizes, test statistics. N goes into the formula for only one of these. It's not effect size. The test, yeah. Your T always has some kind of denominator degrees of freedom, which has N in the bottom of it. So it's number of parameters spent. That is subtracted from your sample size. Now I will say for the unstandardized slopes, the standard error has n in it because it's residual variance n and the variance of the predictor the slope is 4. That's what goes into the standard error. Effect sizes, though, is a way of expressing the size of the unstandardized slope in a standardized way. So, but whether or not the effect size is different than 0 is a function of t, which is a function of sample size. So, like, effect size is sort of like unitless. Like, if I told you had an R of 0.3, there is no way you could possibly know if that was significant because you'd have to know how big the sample was to know that. An R of 0.3 is more different from 0 if you have more people. It's more trustworthy. But R is special in that it ranges from -1 to 1, and so I said R of 0.3 and you all nodded, right? Like that number has meaning. If I told you I had a fixed slope of 6, you'd be like, is that good? I have no idea, because it depends on what the scale of x and y are. And you wouldn't know whether 6 is a lot or 6 is significant. So it's an unstandardized effect. It needs to have an effect size to go with it to put it into some sort of context so that you know how big it is. You also get t, which tells you if it's different than 0, but that doesn't tell you how big it is, because any effect can be different than 0 if you have a big enough sample size. So questions from last time we'll review. What's power? Beta minus 1, yes. Put some words in there, please, but you are correct. What's power? Probability of what?
Finding something that's there.
Finding something if it's there. What 2 things go into power? Effect size and sample size. So it is easier to find bigger effects. It is easier to find anything if you have more people. There's a nonlinear trade-off in terms of which you would want to, basically how those two work together. All right. What's type 1 error? Other one. Alpha. Okay, and now we'll add some words. False alarm or false positive. So what is the other one then, type 2 error? False negative. It's the opposite of power. So a type 2 error is missing something that you should have found. Power is the chance that you found it if it's there. So yeah. All right. Good work, guys. Any questions? No? Okay. Alrighty then. Any questions on homework 3? You're working on it. It's due a week from tomorrow. Not yet? No? Oh, yes?
This might be dumb.
I doubt it.
I can't figure out how I find the estimate for the predicted mean of age group 3. Is that dumb?
It's not dumb. So let me look at that one.
Or like, I can't find the predicted mean for age group 3. Okay. Yeah. Or like 4. I might have just been doing them wrong.
Okay, so this is the same story as last time, same variables, but now using them in models. So the first section is predicting a number of fits thrown. Using an empty model, the number of pleases heard centered at 7. So make sure you're building a new variable to do that. The third model should include a binary predictor for age group centered so that 0 equals 3 years. So that is the way it appeared in your data set. You don't have to do anything to it. So without giving you the answer, so the questions that she's looking at are right here, I think.
Yeah, 18, 19.
Yeah, predicted mean for age 3, the estimate and the standard error. I'm asking you to recognize how that is provided by the model. And so you have to ask yourself, is it already in the model as a fixed effect somehow? Or do I need to find it as a linear combination of fixed effects that are in the model?
Okay.
And the answer to that depends entirely on how age is centered. So if we have age 0 as 3-year-olds, then that is going to be the reference point for the intercept, right? The intercept is the expected y when x is 0. So if x is 0 when age is 3, ...
Okay.
Yeah, follow that logic in your head without giving you too much of the answer.
Thank you.
Sure. Other questions while I have this up? Okay, and so you'll see we're back to a traditional results section. I'm actually sort of wickedly pleased with some of these options here because they're just crazy enough to make sure that you know what you're doing, I hope. But don't hesitate to ask if you have questions. I'm also happy to sit with you and have you work through the logic of these things as you're filling out these things, and I can confirm whether or not your logic is correct. So sometimes that helps to sort of talk it through, especially if you're on the fence about something. I can tell you whether or not the way you're thinking about it is correct. And as always, if you find errors, please let me know so that I can fix them. So, all right. So no other questions right now? Okay, then I will shut this down, and we're ready to move to some new stuff. So the background of this part 1, part 2 is that I wanted to do like one big lecture that had like 4 or 5 different kinds of things that all fit under this heading. And then I ran out of time. So I decided to post the parts that I had done, and I'm still working on the second half. So when the second half is ready, all you'll have to do is add those extra slides to this. There's 1 or 2 numbers in here that is going to be different on here than what you've printed if you printed it last week, because I had tweaked one of the models a little bit, but nothing that matters consequentially. And so the same thing with the example. I thought I could get it all done yesterday, and I ran out of time. So I got you the first half, and then I'll add to it later on. All right, so we are doing general linear models with multiple fixed effects of a single predictor. And now we are officially past where the last version of 6242 left off. So,
Karen.
and we are now into Anova, correlation, and regression. We did correlation before, but we didn't talk about all the kinds they do because they're not all that helpful, but I digress. So we're breaking new territory here. So what we'll talk about is the part one here is the idea of having a categorical predictor with more than two categories in our model. Yeah, so categorical predictor, what does that mean?
Paw Patrol. No,
That's an example.
that's not what it means, sorry.
So it's a variable in which the numbers are just labels, right? So it can be binary, nominal, or ordinal, but the numbers don't really mean numbers in the same way. So this was actually, this part here, I was trying to foreshadow with the tricky question, I should say, at the end of your homework 2, the idea of what is a person's correlation as a linear relationship between the favorite TV show variable and a quantitative variable. Like, was that okay to do? And the answer is no. Because if Paw Patrol is 1 and PJ Masks is 2 and Peppa Pig is 3, like putting a line through that doesn't make any sense because they're not even ordered. Like, you could sort of argue if it was like strongly agree, disagree or something, that putting a line through that is it makes you but it's okay. But no, for something like that, Pearson's correlation can't give you an association. Even if Fitz Throne is associated with favorite TV show, which we discussed. So this is what you do instead. You model it. So reviewing, empty models and single predictor models, the homework that you're working on right now. So any kind of a predictive linear model creates an expected customized outcome from a series of predictors. So we have some kind of constant as an intercept, which is implicitly multiplied by just a 1, a column of 1s if you use the matrix notation for it, plus another constant, a beta 1 times a predictor. This would be another constant, a beta 2 times a predictor, and so on with some kind of error. And so as we reviewed earlier, the specific type of model that we're talking about is a general linear model, which means it's for predicting quantitative outcomes using the normal distribution. So what has to be normal is not the outcome, right? It's the residuals. It's the E. It's what's left over. And so the way that we write that, do you remember what squiggle means? It is a tilde, but what does it mean in this context? Distributed. Yeah, it sometimes means approximate, but not today. So Y for each individual is distributed normally with as the predicted mean or the expected mean for each case. And what's that thing? Residual variance, yes, it's sigma squared E is what we would say that in English. So yeah, just get used to this one. This one's going to be around for a while. Very good. Do you remember the 3 things that these models, basically using them implies about these E values? One of them is normal. Remember the other 2? We talked about this briefly at the end of class a week ago. One of them is a fancy H word. Has to do with variance. Homoscedasticity. Very well done. And if to say that more simply? Constant variance. Yeah. Ta-da! Yes. And the other one? What about the people?
Oh, you're not still doing that?
So heteroscedasticity is the opposite of homoscedasticity. Non-constant variance would be that one, if there's a funnel, like the model works better at some points on the line than others. We don't want that. The model has only one of these values. So it implicitly says, no, there's only one residual variance and everybody shares it. If that's not true, we need a new model. So we have normality of the residuals, homoscedasticity or constant variance, and one more. I'll give you a hint. It's why the class after you is needed.
Generalized. No.
That's next semester.
Which is why.
Yeah, the class that meets in this room afterwards. I know a few of you have friends in there or people in your areas. No? This one starts with an I. I-N. I-N-D. I-N-D-E. I-N-D. Oh, I heard it. Independent, yes, the E's are supposed to be independent. If not, you need a new model. So not only come back next semester, but come back next year too. And actually the EPLS people are my most prominent customers in that class. There are more of them than the people in the quant program. So just saying, mark your calendars. It'll come back at some point. So yeah, if those things aren't true, we need a new model, just to let you know. There are other models out there, and that's why you would pick something else. But all of these concepts that we're learning, like these other models, like take this and add stuff to it. So this is the base of all of the rest of statistics, what we're doing right now. So general linear model that's empty, what does that mean again? No predictors, good. So if you don't know anything else about a person, you give them
Mean.
the mean, there you go. That's it. So when there are no predictors, the predicted outcome for each person is just from the fixed intercept, which means it's just the sample mean. The residual, always defined as the difference between the outcome that's real and the one predicted by the model. That's the same definition. The only thing that changes is what is predicted by the model. And at this point, what we call residual variance, because it's the variance of the E residuals, that's all the variance. So this just gives you back a description of your outcome that's unconditional. Everybody gets the same predicted outcome. All of the possible variance in that outcome is still there. And then what we've done so far is add a predictor. So writing out the difference between the actual model equation, which includes the residual, and the one that's predicted for each person, which doesn't. So what this means is that anybody who has the same X has the same predicted Y. So it's still kind of like a mean in that it's across people, but it's conditional on your value of X. So the intercept, expected value of outcome when X equals 0, so that's why we center, so that X equals 0 makes sense. The slope of X, the difference in the outcome for a 1 unit difference in X. Residual, same definition. So after we put in a predictor, if this predictor matters, the E residual should be smaller because it's a better line that goes through the data, and then we get a new amount of variance that is left over. And so that, when people say residual variance, the term residual also means leftover. So just keep that in mind. I'm going to try to differentiate these things because on your output, even if it has all the variance in it, it will be like residual variance. So I'll say that this is left over because some of it went away after we added X. Or this represents the unexplained variance by X. Okay, with me? Okay, any of that you want to hear again before we jump into the new stuff? Okay, let's jump. Oh, not quite yet. One more review slide, then we jump. Forgive me, I don't have my slides memorized yet. So unstandardized slope. In terms of what we would care about our beta 1 slope, we get an estimate, most likely value given the data. We get a standard error for it, which is an index of imprecision with an M. In the same way that we had a standard error of the mean, that was the average deviation of the sample mean from the population mean, we get a standard error of the slope, mark question, which is the average deviation of the sample slope from the population slope. So it's the exact same logic. When there's only a single slope in the model, its standard error is a function of the model's residual variance, that's up in the numerator, the variance of X in the denominator, and denominator degrees of freedom, which works out to be sample size minus K, the number of fixed effects, the number of betas. So think of it as the number of things you had to estimate in order to create a prediction for each person. So far we've had a beta 0 and a beta 1. So degrees of freedom left over is based on N minus K. We can take estimate, divide it by the standard error, and that shows up as a T. If we use the T distribution and denominator degrees of freedom, we'd call that a T-test for it. If we don't use denominator degrees of freedom, which in some software packages that is true, it's called a Z instead. So have you heard of M+ software package, for instance? You have? Okay, good. So this is an example when literally the exact same number, what you would get from estimate divided by standard error, they label it a Z because they don't use degrees of freedom. They assume infinite. And so they use the Z distribution instead of the T. But it's the same idea either way. So one other piece of information that you would want to provide is a standardized version of the slope. And I'm asking for that in your homework. You can use GLM select as one way to do it, as also reg for regression. That's another one. And that is the standardized version of the slope where you're correcting the unstandardized version for the distributions of x and y. Yeah.
Can you explain the difference between these two just a little bit more? Like, why would you want an unstandardized one in the first place? Because standardized just sounds better. Just like logically.
Okay, so two reasons. One is that you're trying to predict the outcome in the scale that the outcome has. So like it's, pounds, inches, GRE scores, right? And so like you want to be able to do that in a prediction sense. The other is that this concept starts to get a little bit weird when you have more complicated models. So for instance, one of the things we'll get to towards the end of the semester are interaction terms between predictors, where the slope of one predictor then varies as a function of the other predictor. And it turns out that if you take each predictor's slope and standardize it and multiply them together, you get a different answer than if you take the multiplication and then standardize it. So this falls away on more complex models because there just isn't a clear way necessarily to do this in models that have more than one type of variability in y when you have dependency. So this is the scale of the original data. This is one way of thinking about it in a metric that is more intuitive. There are others. So beta as standardized is R. It's Pearson's R that you know as a binary, bivariate relationship when there's only one x, but it's another kind of R if there's more than one x. And there's also something we're going to learn today called D, which is another version of the standardized statistic. Does that help?
Yeah.
Okay.
So like standardized is easy until it's unuseful.
Pretty much.
Okay.
Yeah, it starts to, this little
It gives
formula.
units a name.
What?
And so basically like it gives units a name.
Yeah, it's a way to translate the slope into a number that anyone would know what to do with, basically, rather than 6. 6 good? So, okay, other questions? All right, then moving on to categorical predictors beyond just binary. So the first thing here we've already done, just to remind you of what it looks like when you have a binary predictor. If you only have 2 groups, then there's only 2 means to be recovered for the outcome. And so you only need 2 fixed effects to do it. If you already have an intercept, trying to put this down carefully, that one, then all you need is 1 beta 1 to capture the difference between the 0 group and the 1 group. So in terms of this model right here, this equation, beta 0, the intercept, is always the expected outcome when x equals 0. Under this coding scheme, this would be the expected y for group 0. So if I tried to trace through the logic here, substitute in the value of group for which I want a prediction, it would be beta 0 plus beta 1 times 0, so that part falls out. So the mean for the reference group, as it's known, the group where the predictor is 0, is just the fixed intercept. So that's one of our fixed effects. The group 1 mean, which is known as the alternative group, that is a function starting with beta 0 also, but then adjusting it for the fact that we now have group equals 1 and we pick up the effect of the slope. So if you want to know what the mean is for the alternative group, it's the mean for the 0 group plus the difference between the groups. You start with the 0 group plus how it differs from the 1 group, you get to the 1 group. So this is the age group with the 3 and 4-year-olds. I'm looking for this sort of logic to play out in your head. And then the other thing you would want to know besides the 2 group means is the difference between them significant? And so if you follow through the logic here of how each group gets its own mean from the model, we have group 1 here. Group 1's mean comes from beta 0 plus beta 1, the equation right here. Group 0's mean is just beta 0. So if you just do the math, the beta 0's cancel and you're left with beta 1. So even though there are three things that we want to know, we only need two fixed effects. The third is determined. And there are other ways of coding this so that what you get are the two means directly, and the mean difference would be a linear combination. I don't want to confuse you by showing those other things, but just know that you always need one fewer fixed effect than you have, fixed slope, I should say, than you have number of groups. If I have two groups, it's two fixed effects. That's all I need. One slope and one intercept. So if you have more than two groups, you need more slopes. So number of categories with a capital C. If I have a categorical predictor with three categories, three groups, those words are synonymous, by the way. I'm trying to say categories, but sometimes I slip into groups. If you have three categories, then we're going to need the beta 0, and we're also going to need a beta 1 and a beta 2. So that works out to be 3 fixed effects for the 3 categories. Likewise, if we had 4 categories, we still need a beta 0, but now we need 3 slopes. 4 fixed effects for 4 categories. How many fixed effects would we need for a 5 category variable? 5! 6 categories? 6. Yeah, that's it. So by the way, this is analysis of variance. Anova, as it's called. All right, so here is an example that we're going to see in SAS and Stata using the same GSS data. They had a variable that was self-reported respondent class. So they asked them like low class, middle class, upper class, that kind of thing. And within the subsample that were complete on the variables that I'm building into this example, this one may be backwards. It was 287 the first time I ran it, and then I switched it, so it's 278 now. I have 436 people in the low group, 278 in the middle group, and 20 people in the upper group. Note, this is a new thing. Little n is sample size within a group, within a category. So if I were to add these numbers together, 436, 278, 20, that gets me to big N. That is a common convention. So what I need to do is to set up a coding scheme by which each group can get its own mean. So just as before, somebody has got to be the reference group, the 0 group, for when intercepts are 0. It does not matter which one you pick. I just picked low because why not? It's the biggest one, it came first, bleh. There's no good reason. But these are 2 new variables, L versus M and L versus U, that are going into the model as my predictors. So here's the coding scheme. The low group is going to get a 0 on both of these predictors. That means that the intercept of the model beta 0 is now going to be the expected outcome specifically for the low group, because that is when all the x's are 0. From there, we need to tell the model how to differentiate the low group from the middle group, as well as the low group from the upper group, because low is the reference point. It's the you are here sign, so everything is relative to it in the model. So the first variable I've created where the middle group gets a 1. So if all I had were low and middle, then that's all I would need, right? That's what we had before when we had a binary variable. The other alternative group, the upper class, gets a 0. I swap this coding scheme for the second predictor and give the upper the 1 and the middle the 0. So when these 2 predictors are included together, that's the key word, together, simultaneously in bold font with an underline, then you can interpret each of these variables as I put here in the label. The first variable, L versus M, carries the mean difference between the low group to the middle group. The second predictor carries the difference from the low group to the upper group. Now, why I'm harboring simultaneously, what would happen if I tried to put these in one at a time? So here, I'm doing this. Pretend I only have the first row here. Look at where the 0s and 1s are and tell me what that variable would do. Can you guess? It's going to lump together the zero groups, right? So this would give me, if the first row here, low versus mid, if that were all by itself in the model, it would give me the difference of the middle group versus the average of the low and the upper. That doesn't make sense. So considering that you would get the middle versus low and upper, the next variable steps in to then separate low and upper. So it fixes that ambiguity. They go in together. This system of giving people zeros and ones is what's known as dummy coding. So if you read a results section saying we had a dummy coded predictor, that's what they mean. So let's work out how the model tells us what the mean for each group is and how the groups differ from each other. So this requires understanding which of those terms are directly given by the model and which ones are implied by the model. So there's 3 means that we want to know, one for each group. There's 3 possible mean differences that we want to know. So we'll start with the low mean here. So I'm filling in this equation here for predicted y hat. So how does the model give us the predicted outcome for the low group? Well, y hat for low starts off with the intercept like everybody. When group is low, this predictor L versus M takes a 0. When group is low, the second predictor L versus U also takes a 0. That's the coding scheme up here. Yes?
No, it's like sorcery.
Well, no, but you're
I'm seeing. No, I'm following.
but you're the
That's why my face
witch,
did that.
right?
Yeah.
You're the witch because you set this all up. You
Exactly.
know what
Yes,
was
this
going to
is-
happen.
Math is interesting.
I know, right?
Not to be a suck up. I just told them it was a sucky up thing. I don't know. I was like, oh.
No, but in all seriousness, like I did math in high school and I got to college and I was like, I don't need this crap. And then I'm like, oh my God, it's coming back. Like it was so much more interesting when there was a reason for it than when you were just like answering problems about trains and shit. So yeah, it's math, but like on purpose for reasons. So yeah, so once you fill in your 0, because they're not the middle group and they're not the upper group, beta 1 and beta 2 drop out. And so you're left with just beta 0 as the interpretation. So beta 0 is the mean for the low group. Now how do we start there as the you are here sign of the map of our data and get to other groups? Middle mean. This one is not given directly by the model, but it is implied by the model. It is a linear combination of model fixed effects. So that's what implied means. So middle group means start out with the intercept. Everybody gets the intercept. Now beta 1, it takes on a value of 1 when you're in the middle group, so we're going to pick up that as part of our prediction. But low versus upper takes on a 0, so that one drops out. So it's beta 0 plus beta 1. That gives us the middle group mean. Likewise, for the upper group, start out with the intercept. Upper group takes a 0 for the first variable, so beta 1 drops. It picks up a 1 for the second variable, so that stays. Linear combination. Now the differences. Difference of low versus middle. So the way that I word this, and you'll see this in your homework by the way, I'm saying that low versus middle is going to be the first term, and then low is the reference. So like the reference is always a thing that's subtracted. So middle is beta 0 plus beta 1. We figured that out earlier. Low is just beta 0. So the beta 0s drop, and I'm left with beta 1. So the difference between low and middle is given directly by the model as beta 1. That's what it means. Likewise, if I have low versus upper, upper is beta 0 plus beta 2, low is just beta 0. Beta 0s drop, then the difference between low and upper is beta 2. And so this is why I phrase it as low versus upper. Beta 2 is how far off upper is from low, because low is the reference point. So if beta 2 is positive, upper is higher. If beta 2 is negative, upper is lower. Upper is lower is maybe the most unfortunate sentence I've said in a while, but don't worry, that's not going to happen. Spoiler alert, being upper class means you have a higher income. Well, it's self-reported, right? They know how much money they make. They pay taxes. Well, I didn't say they pay a lot of taxes. I said they pay taxes. They pay someone so that they don't have to pay a lot of taxes. How's that? Yeah. Okay, so we got so far what's given by the model directly. The low mean, how low differs from middle, and how low differs from upper. Now the last difference is also a linear combination. So we have upper as beta 0 plus beta 2. Middle is beta 0 plus beta 1. Now the beta zeros drop, but we're still left with two betas. So the missing comparison is beta 2 minus beta 1. Anything that is a linear combination of betas, you have to ask for to get.
Can you say that one more time?
Mm-hmm. Any term, any piece of information here that is a linear combination of betas, you have to ask for extra to get. This is something that I wish I had learned initially, and that's why I'm giving it to you. The other way to get those missing pieces that are linear combinations is to recode the model and run it again. But I think that is potentially more confusing because then you have to keep track of what things mean as you changed what they mean. So I'm teaching you this because it's streamlined. So it reminds me of those logic problems. Like, you know, I had these on the GRE, but you guys didn't have that, I think. Or maybe you did. It was analytics section. It was back in the day. It'd be one of those things like, you know, Bob is 6 years older than Susan, and she's twice the age of Greg. And you got to figure out how old everybody is. And once you know one of them, you can figure out all the others in relation. Like, this is like that. All I got to know is beta 0, beta 1, and beta 2, and I can figure out everything else because they're all relative to each other. So if I wanted to, I could code the model in a different way that got rid of the common intercept, and I could just give each group its own mean. Then the model would give us the three means directly, and any of the differences would all be linear combinations. Some people like to do it that way. If you get to design of experiments with Dr. Aloe, he'll spend a week talking about that. So you have the flexibility to set this up however is most convenient. Far and away, this is where most people learn and stop. So it's a good place to start. I don't want to confuse you too much by switching around the coding, but just know that this choice you make, right? This sorcery is of your own making. Okay, how are we doing? Okay, now how do you ask for this stuff? That's the question. So this is what it would look like in SAS. I have the same slide in Stata next. So I am going to show you the Stata one first because it looks more like the equation. So what we just went through is at the top here for your reference. So in Stata, the GLM analog is the outcome first, and then the predictors. C dot distinguishes predictors that are continuous. Predictors that are something else that we haven't gotten to are going to be I dot. I believe this is a default, but I tend to write it just to be clear. The rest of these things you saw one example of on your last homework in example 4. Now you're going to see more. LinCom stands for linear combination. So I have written out how you would use these things to get all 6 pieces of information. The 3 of these are redundant. I just did it for pedagogical purposes so that you could see the pattern better. So the first 3 equations up here, how does each group get its own mean? Well, it starts off with beta 0 for everybody. So beta 0, and then I have a times 1 indicating that it is turned on as part of everyone's predicted value. And this underscore const, what does that stand for, Stata people? Constant. Yeah, I hate that word, but that's what they call it, and I can't change it. I can't even put this in capital letters or they won't run it. So then we fill in the variables, right? So we have the part that's in parentheses here. So the words themselves refer to their betas in the model. That's what they mean. So in the first line here, I am creating prediction for the low group. The low group is scored 0 in both of my predictors. So 0, 0. So this first line is completely redundant with beta 0. And you can see that if you look at the coefficients, there's only one thing in here. It's not really a linear combination. Second one and the third one are linear combinations. They are not model parameters. They are implied by the model parameters. So the second group, the middle, starts off with a constant. It picks up beta 1. It does not pick up beta 2. So literally the values that are going in here is what's in parentheses. The value of the predictor for which you want the predicted outcome. Last group, upper group, constant, no beta 1, pick up a beta 2, we get there. Then the differences. So this is one of a common rookie mistake that I'll highlight here. There's a reason I spaced this over to make a giant hole right here. Constant. If what you're asking for is a difference, a slope or a difference between groups, constant does not go into that. Constant drops when you're comparing two groups that are not part of the reference group. So no constants here. When you're comparing two groups anyway, I should say. That's holds. So the first lincom here and the second one are not actually linear combinations. They're the ones that are given by the model. So low versus middle is the beta 1 here. Low versus upper is the beta 2. And if I want the difference between the two, I switched it so the predictors are in the same order, but it's beta 2 is the positive one minus, so I'm literally putting a minus in here, beta 1. So I'm writing it as a linear combination. I could have up here written minus beta 1 plus beta 2, but it's the same difference. So the direction is what will be different depending on who you give the minus to and who you give the plus to, but the significance and the standard error will be the same. So to recap, when you put these words in here, the names of the predictors, you are asking about their betas. You are asking it to do math using those estimated fixed effects. Question? Cool, huh? Did you know that you could make it do math for you? Beyond just, the stuff it's already doing? So the idea that you are building a linear combination of betas multiplied by predictors, constant times variable plus constant times variable, that is made explicit in Stata. The same exact thing in SAS drops out the mathematical operators. So rather than saying times 0 or times 1, you just put the coefficient after it, and you don't put pluses in between. So everything else looks exactly the same. Just note the bottom here. This is an implicit subtraction. It's L versus U minus L versus M, which is the same order than this is L versus U minus L versus M. Okay. Yeah. How are we doing? Good. Okay, you want to see some numbers? That help? Go back over it with numbers in there? Can't hurt, right? Then I can show you where they came from. So two models on this slide. Empty model. So the variable that we're predicting now is personal income. I didn't realize initially, but there's two kinds of income in the database. We were looking at family income, and I was interested to see that people who weren't working still had a really large family income. And I'm like, oh wait, duh. So I switched to personal income. And so we're going to look at how things like education and other characteristics predict personal income. So the empty model, two predictors. One fixed intercept beta 0 and the variance of the E residuals. So the intercept takes on a value in this model of 17.3. So that's the sample mean income, personal income. The residual variance then of 190 is all the variability in personal income that there is to be had. So reminder, what is variance? More question? Yeah, what's the mathematical definition of it? I'll start you off. It's the squared something.
Standard deviation.
Squared standard deviation. And standard deviation is what? From the mean. What from the mean? The average deviation of what from what? Well, because there's two different things that have that same phrasing. There is the average deviation of each observation from the sample mean, and there's also the average deviation of the sample mean from the population mean. Which one is this? This one? So there's two numbers up here, right? Standard error is the second one. This is how far off the sample mean it should be from the population mean on average. This number is variance, so we know it's squared, but it's the squared how far off is each person from the sample mean. Squared. So standard error is like standard deviation in that it's unsquared. But it's referring to the intercept, whereas this variance is referring to the people. So the model then, it gave me these numbers right here. Estimate of 13, standard error of 0.6, that's the intercept. It gives you a p-value for it, but that would just say whether or not the mean of 13 is not 0, which, okay, whatever. Then the two slopes. How does the low group, intercept 0, differ from the medium group? The estimate is 8.8. Who's higher?
We're talking dollars, right?
$1,000.
So it's like that FAM Inc.
But this is,
1,000, but this is personal.
yep.
That okay.
So this is $8.8 thousand. Who's higher? So look at the coding, look at the sign. Beta 1 is a mean difference between low and medium. That's what that variable means. Who's higher?
So there's more difference between middle class and upper class than there is between lower class and middle.
Nope, that's too complicated. This is one difference between two groups. You think the low group's higher? You don't know? Middle, yes. Yeah, so if you look at the coding, who's the one? Middle. The coefficient gets the one gets the coefficient, we'll sit it that way. So 13 is the expected income in thousands of dollars for the low group. As you move off of that 0 point and you go to 1, you pick up $8.8 thousand. 8.8 divided by 1 is a t that is like 8, which is way out there in the right tail, p less than 0.01. Likewise, low versus upper, look at the coding. Who's higher? Upper. So then we have low differs from upper by 10, which is significant. So then the things that we don't know, the middle mean as a linear combination, we get that from beta 0 plus beta 1. Upper mean as another linear combination, we get that from beta 0 plus beta 2. And then the difference, 10 minus 8 is 2. So it's literally the difference of these two numbers is the difference between the two non-reference groups. Now I want to point out something that is interesting potentially, the difference in these standard errors. So the standard error for the low group is 0.6. The standard error for the middle group is 0.78, but the standard error from the upper group is 2.9. Why is that?
It's the further you get away from the mean, the less predictability we have. It's harder to.
In this case,
Like
yes,
a funnel
the
thing.
further you get away from the mean, the less The more imprecise the prediction is, but that doesn't account by itself for the difference in these standard errors.
When we talk about money in our country, we have such high outliers that that's my guess, is that like, it's
It is
it's throwing
skewed.
off.
It is skewed, although I cut off the super rich people to make it less skewed.
It's our sample size.
Ding! I got 20 rich people here. So, in terms of precision as to guessing what their mean is, it's way less precise. The standard error for it is going to be way bigger. So that's why when you look at these numbers, like 10, that seems like a big difference. 8, that seems like a big difference. And if I want to know if these two numbers are different from each other, I can't know that without also considering the amount of precision that goes into each of them. And that last comparison there of 2 is actually not significant. The third group's mean is just too imprecise. Yeah.
Excuse me, at least how you got the middle mean and upper mean there standardized.
Ah. Magic. No. Do you know how I got this? There is a formula. I'm not going to bother to give it to you. I asked SAS to give it to me, and it did. That's how. And that, by the way, is the reason for actually learning how to program this stuff, because you can do the math to figure out what the implied mean is from the coefficients, but that same math can't give you the standard errors and p-values that go with it. Yeah.
Is the residual variance number in a unit that we understand?
It is only meaningful relative to what it was before.
Okay, so it's 190 watts, we don't know.
It was 190, now it's 171. So
It's getting smaller, which is good.
that's right. Thank you for, that was such a nice segue into the next thing. Did you like read ahead?
Certainly not.
But yeah. So yeah, it was 190, now it's 171. So some of it was explained. It looks like upper and middle are different from low, but upper and middle are about the same. So then the question is like, well, okay, then what does that mean? Well, let's see, and it comes into a comparison of these two numbers. So before we do that part, do you want to see the SAS code that goes with this, or do you want to talk about that? Take a vote. Do you care? What do you want to do? Want to talk about that? Okay, we'll talk about that. We only got 10 minutes left anyway.
Wait, does that mean we're not going to talk about this?
The question was order.
Okay.
Yep. I actually gave it to you already, but you'll see this in the handout.
So that was the state.
SAS code's right there. Yep. Yep, that's what it will look like. But so yeah, so we have these things are known as pairwise comparisons because they are differences between each pair of groups. If you have 3 groups, there are 3 possible comparisons. But that is a specific answer. If you want to know if your model is any good overall, a more general answer like, does respondent class matter? Right? Are there any differences across these groups? Like, does group matter as a question? Then we haven't answered that question yet. Answering that question requires us to consider something else, which is the foreshadowing that you just did. Is the residual variance from this model that now has 2 predictors in it significantly lower than the total variance we started with? Saying this differently, does y hat, the one that is predicted by group membership, significantly correlate with y? So this is a difference in concept. Previously, y hat and x were the same thing because only x went into y hat. So they were on different scales, but they were functionally the same variable. They had the same information. Now y hat is built out of 3 pieces of information, the intercept and the 2 group differences. So it's still the same idea of linear relationship, but now what it is between is the outcome and the predicted outcome by the model. So that's what we want to know. So this is 2 different ways of saying it. Is our variance significantly reduced, meaning we have significantly explained some of it, such that we would say there's a significant correlation between the group predicted outcome and the real one? So to answer this question, we have to consider the complexity of our model relative to how good it did at explaining this residual variance. So we are picking up a new technique, multivariate wald test. So a univariate wald test you already know. You get one of those for each slope. That is the t-value that comes from estimate divided by standard error. So if that t is significant, you know that that one slope is different than 0. This is a different question. We're asking, is the model prediction quality different than 0? And that requires combining the slopes together to answer that question. So we have a degrees of freedom, numerator, denominator. And you'll see where those terms come from in just a second. Numerator is how many points you had to spend. So it is the number of fixed slopes in the model because we sort of assume you always had to spend the intercept. That's part of the empty model. So besides just putting the mean in, how many other terms did you have to put in? How many other fixed effects? So I'm trying to be careful with language because it's really the idea of how many fixed slopes you had to put in, not how many predictors, right? So in our example, we're thinking of this variable, respondent class, as one predictor, right? That's one idea. But to put it into the model, it takes 2 slopes. So we got to know how many slopes we're using, not just how many predictors conceptually are represented in them. So denominator then is how many points left over that you haven't spent, and minus the number of points and 1. In GLMs, the amount of information that is provided by the prediction and the amount of information left over is quantified somewhat differently. It's the numerator of what we would call variance. This part right here is called sums of squares. So you have seen this before in the formula for variance way back in the day. We said how far off each observation is from the sample mean on average squared, right? That's variance. The on average part comes from dividing by n minus 1. So this concept is just the numerator. It's like the collection of offnesses, but not the average one. So it's hard to conceptualize. I'm going to try to use the word information to separate it from variance, because variance is adjusted. It's like an average information. This is just a collection of all the offnesses of various kinds. So we have model sums of squares that quantifies how much information the model captured in the outcome. It is the difference for each individual of what the model says their y should be versus the sample mean. So if you think about the prediction of a sample mean across a bunch of variables, it's flat, right? Like everybody gets the mean, the end. So this is like, how much better did you do by giving each person their own y hat relative to just everybody gets the same? So how much extra information have you picked up by customizing your outcome with your model? Customizing your predicted outcome. Then we want to know, well, okay, so you picked up a lot of information, great. How many slopes did it take you to do that? Because I could build a y hat with 2 slopes or 200, right? But so if I put in 200, this better be really good. If I put in just 2, like the standards are lower. So that idea of like how much effort did you have to put, we call that parsimony in statistics. That's the sums of squares. So this part here, the numerator offnesses divided by the number of degrees of freedom. So it's not variance, it's more like information per point spent. The rest of it, though, what's left, then is what you used to thinking of as variance. It's the difference, the sums of squares residual is the numerator of variance. It's the difference between the actual one and the one that's predicted by the model. So it's everything that's left. So if you think of the total deviation of one person's outcome, like part of it is explained by where the regression line ended, the rest of it you don't know then is the residual. So it's like it's dividing that total variation into known and unknown. So putting it together, we end up with a table in your output that I've told you to ignore up to this point that you now need to pay attention to. So we have 3 columns here. Sums of squares, that's like information. Degrees of freedom per point spent. Mean square is sums of squares divided by degrees of freedom. So you're already familiar with this idea of residual variance right here. Mean square residual, that's where residual variance is. That is the amount of variability left over. The amount of information, so to speak, that your model captured is above it. That's mean square model. So then we end up with a measure of effect size for the overall model, which is known as R square. And the formula for it is right here. It's the difference between the sums of squares you started with for the overall variable minus the sums of squares that are left after your model did its thing relative to what you started with. So it is roughly equivalent to, but not exactly the same numerically as just saying, what is the proportion reduction in variance? Like if I had in the previous numbers here, let me go back to this, like if I had 190 and now it's 171, it's roughly 190 minus 171 divided by 190. Like how much percent has this gone down? It's so close, but it's not exact in this case. In every other model that follows after these models, that's exactly what we do instead. We just look at the proportion reduction. So that thing is R square. Yeah.
So SSY is the SS total?
Yes, damn it. I forgot to switch it out of here. I switched it to, I was Y for once and then I made it total. Thank you for catching that. I'll fix it later. But yeah. So R square is the square of the correlation between Y hat and Y. R square is the square of the correlation between the Y your model says you get and the one you actually got. And we end up with a significance test for it. Rather than T, it's our new friend F. And I've given you 2 formulas for it down here. F is telling you whether or not your R square, whether or not your reduction in variance is significant. Whether or not your 2 slopes together are not 0. And here's F. So we're out of time, but I'll let you marvel at it. It looks a lot like chi-square. However, it looks more like T in that its shape depends on sample size. T squared is F. So that's why up to this point I never had you worry about it, is because if your slope is significant for one predictor, you know the model is significant because T squared is F. But now we got 2 T's, so it's not just a straight T squared is F. So now you have another letter to add to your collection.
Good.
I know, right?
This is like
Well, at least this is an English one, right? It's not like squiggle or squiggle with a tail on it, you know, whatever the hell that one is. So exactly. So we will pick this up on Thursday. In between then, let me know if you need anything, and I do have office hours here later on today. So see ya.